First of all, I'd like to say thank you for organizers of this meeting today. And now I hope that my report will be quite simple. So I'll try to make it simple. Let's start. It's devoted to extendable symplectic structures and the inverse problem of the calculus of variations for system of equations in extended Kovalevskaya form. As we know, symplectic structures of differential equations are similar to symplectic structures in Hamiltonian mechanics, and they can be described in terms of variational analogues of differential two forms, and also in terms of equivalence classes of linear differential operators in total derivatives. But such operators are defined on infinite extension of differential equations, and they are allowed to be degenerate. On the contrary, the well-known inverse problem of the calculus of variations can be also formulated in terms of linear differential operators in total derivatives. However, in this case, such operators are defined on jets, and they must be non-degenerate in some sense. I hope that today I will make this sense clear for the current report. Fortunately, restrictions of operators which are related to the inverse problem of the calculus of variations to the corresponding differential equations are always related to symplectic structures. So, is it everything okay with the presentation? Can you see it clearly?
Yes, it's okay.
Okay, thank you very much. So let's begin with some definitions and some notations. Let we have a locally trivial smooth vector bundle over a smooth manifold X with its dimension, X dimension is n-1, and the dimension of this bundle is M. Denote product of X and real line by M, and the product of E and the real line by N. Consider the projection to the first multiplier, and denote the induced bundle by pi. This construction is similar to a construction of evolution system of evolution equations. So it's nothing new here. We also need to we also will consider the model of sections of the induced bundle, of the corresponding induced bundle, which is denoted by kappa of pi. And now we begin to talk about local coordinates. Let's choose local coordinates x1, xn-1 on the base x, and u1, um along the fibers of the bundle C. Choose a global coordinate there on a real line, and denote it also by xn. Then x1, xn are local coordinates on M. Let alpha be a multi-index. Here, its components are non-negative integers, and we will denote by alpha x the formal sum of the form which is presented here. Put absolute value of alpha as a sum of its components, and usual notations for differential operators of total derivative for their composition. Maybe it's a little bit non-usual notation for coordinates, u with upper index e and lower index alpha x, but today it will be convenient for us, I guess. So d with the lower index xe are operators of total derivatives, d with their index is the identity operator, and further we consider only adopted local coordinates on infinite jet space. That is local coordinates of the form x1, xn, and u with upper index g and lower index alpha x. Such coordinates only. We consider such coordinates only. So let B be a vector with m components, where all components are positive integers. Further, we assume that either all components of this vector are equal, or a bundle has a trivial structure group, or bundle C. Then we can define system of equations in an extended Kovalevskaya form. What does it mean? Let we have a section phi and be such section that its components depend on independent coordinates and coordinates of the form u with upper index k and lower index alpha x for which holds alpha n's is less than b case. Then a system of equations, which is presented here, is written in an extended Kovalevskaya form. In effect, it means that derivatives with respect to t, with respect to xn's, in the right-hand side has lower order than derivatives on the left-hand side. It means exactly that this system of equations can be represented in the evolutionary form, in the form of a system of evolution equations, by introducing some new dependent variables. We assume that section, which is difference between u with low index bt minus phi, determines smooth submanifold of the corresponding jet space. And it means also that its finite extension is a smooth submanifold of the corresponding jet space. In effect, because of the form of this system of equations. Denote by epsilon the infinite extension of the system of equations under consideration. And further, we consider only systems of equations of this form, which infinite extension had the following form. By external with respect to epsilon coordinates on jets, we will mean local coordinates on the left-hand side of the equations of the system epsilon. Other local coordinates on jets are internal with respect to epsilon. They internal with respect to epsilon, but still they are local coordinates on jets, not on epsilon, in effect. So here on this page, we can see a formal theory, formalization of some construction, which I will explain now. So we need to introduce one construction, which I call the prime system, and it's denoted with primes everywhere. It's analog of a tangent bundle, but this form of tangent bundle, in fact, it's another form of tangent bundle. This form of a tangent bundle is more convenient for our discussion today. So consider another one projection to the first multiplier, and its induced bundle. This construction is similar to the construction we saw when I said that this construction is similar to construction for evolution systems of equations. So again, denote by m with prime product of m and real line, n with prime is product of n and real line. Then dimension of the base of this pi prime bundle becomes n plus 1. Is greater than n, it became n plus 1. And let's choose another one global coordinate on the real line. It's denoted by a here. So we have two global coordinates on the real line. We have a global coordinate t, which is similar to evolution equations, and another one global coordinate on a. This global coordinate, in some sense, it's a formal consideration. Let's consider system of the initial system of equations, and let's assume that we have another one independent variable in which then equations of our system depends on this variable implicitly. So denote k jet of a section at a point x a by the following. Use the following notation for it, and it allows us to define two maps. These two maps are useful for our further consideration. Just formal construction. So let's talk about the main idea of this construction. Here we have a way to lift. In some sense, it's an analog of the lift. This map f with prime is analog of the lift to the tangent bundle. This construction, which is I call by prime system, is a system of equations in which is described in the remark 1. It's a system of equations f with prime of u bt equals to f with prime of phi. This system of equations also has an extended Kovalevskaya form. So the main idea is to introduce another one independent variable, and consider initial system of equations with another one independent variable. Just formally consider such system of equations. Then its infinite extension becomes greater than infinite extension of the initial system in some sense, because we have another one total derivative. It's derivative with respect to A, and its infinite extension contains also equations of the form derivative of with respect to A of the left hand side equals to derivative with respect to A of the right hand side. And we can note that derivative with respect to A of the section F with prime equals to linearization of a section F with prime, which is applied to a section U with prime with lower index A, which means derivative with respect to A. So then system of equations epsilon with prime is similar to the tangent covering of epsilon in this sense. Here coordinates U with prime with derivatives with respect to A of U with prime play role of fiberwise coordinates Q from the tangent covering, which can be represented as F equals to 0, linearization of F of Q equals to 0. So we have the following situation. Now we can introduce some maps which are analogs of the lifts for tangent covering. Denote by F lambda homomorphism from horizontal n forms of pi to horizontal n+1 forms of pi prime, which is induced by the following map. Omega maps to wedge product of differential of A to pullback of omega with F. So we have a differential operator, usual differential operator from a model of induced model of sections of the induced bundle to its adjoint model. Here by adjoint model we mean model of homomorphisms from kappa of pi to horizontal n forms. So we have a differential C differential operator denoted by A prime, a unique C differential operator such that for any lambda and mu from kappa of pi holds the following relation. In effect, it's analog of a lift of operator A to a tangent covering. Here we have the natural pairing between the model and its adjoint, and then one may say that A prime adjoint to A prime operator is a prime operator for A adjoint. So prime and adjoint are commute in this sense. We also can define a map, an analog of the map of element G of kappa with hat of pi from the identity which is presented here too. It's just formal constructions. Further, we use notations with primes for local coordinates on n prime, and we know that functions U with prime, derivatives of the U with prime with respect to A determine a section of kappa of pi prime, and in local coordinates, this correspondence between phi and phi with prime in local coordinates, they are identically equal up to primes of arguments. So in local coordinates, nothing is changed in effect. And in local coordinates for a C differential operator A is nothing changed too, but here we have n+1 dimension of the base, and that's why it became another multiplier of the form of the wedge product form. Here we have, instead of dx1 wedge product by and so on by dxn, we have differential of A wedge product to differential of x prime and so on. But corresponding functions A alpha EG and A prime alpha EG are identically equal up to primes of arguments. So in local coordinates is nothing changed. Nothing is changed. So let's recall what we will mean by symplectic structure. Let we have a C differential operator which is restricted on the system of equations of an infinitely prolonged system of equations, such that the following relation holds. here delta adjoint to delta with composition of the adjoint operator to delta with the linearization of system of equations equals to adjoint operator to the linearization and this with composition with delta. One can consider an equivalence class of delta modulo operators of the form square composition with L epsilon, where by square we mean a self-adjoint operator. Then a group of symplectic structures of system of equations consists of equivalence classes of such operators, which are related to closed variational two forms. In effect, we need not today for a concrete relation, we need not to discuss this relation in details. It's just enough for us to know that each variational operator, each solution for the inverse problem of the calculus of variations is related with a symplectic structure. In effect, group of symplectic structures, each symplectic structure can be represented as an equivalence class of C differential operators which satisfy this relation. Let's introduce a definition. A C differential operator A adjoint is said to be a variational operator for a system of equations, for the initial system of equations, or equivalently for its infinite extension, if for some Lagrangian holds the relation, the result of A adjoint of F equals to Euler operator of Lagrangian L. So there should exist some Lagrangian such that our operator A adjoint make our system of equations as an Euler-Lagrange system of equations. It becomes Euler-Lagrange system of equations. And by a variational extension of the operator delta of arbitrary operator or of a symplectic operator especially, by variational extension, we will mean such operator that its restriction coincides with delta, restriction to a system of equations, and its adjoint is variational operator for a system of equations. Recall that variational operators are defined on jets, not on a system of equations. Let's introduce second definition. A symplectic structure of epsilon is extendable to jets or just extendable if it is generated by some operator which admits some variational extension. It means that by an extendable symplectic structure, we will mean such symplectic structure which can be represented by a differential operator which admits variational extension. So it's not a definition of a non-degenerate symplectic structure in some sense, but there we will define a symplectic structure with non-degenerate extension. An operator from this definition is also an extension of the corresponding symplectic structure, and we will say that extension of a symplectic structure or equivalently a variational operator A adjoint is non-degenerate if the system of equations A adjoint of F equals to 0 has a differential consequence if F equals to 0. Then for some C differential operator holds F equals to B of A adjoint of F. It follows from the fact that each finite extension of the corresponding system of equations is a smooth submanifold of the corresponding jet space, jet manifold. So let's consider two examples of extendable symplectic structures with non-degenerate extensions. First example is one-dimensional shallow water equations over uneven bottom in Euler's variables. Each has a form which is represented here. One can use equations of this system of equations, first and second equations, for introducing non-local variables. In effect, it's abelian coverings. One can introduce a non-local variable W by the relations which are presented here, and consider the equation for the potential variable W. It's so-called SVP, system of equations. This equation admits a variational operator, identical variational operator, because it's an Euler-Lagrange equation, in effect. And one can also introduce Lagrange's mass variable from the relations which follows from the second equation of the system of equations. and consider shallow water equation in Lagrange variables for this mass variable. This equation can be written in an extended Kovalevskaya form also, if we will. Oh yes, okay, it can be, by obvious way, it can be represented in an extended Kovalevskaya form. This equation admits a variational operator which equals to derivative of m with respect to x in the raised to the power minus 1. So using both mentioned conservation laws, we obtain a backward transformation of the equations for potential variable and for mass Lagrangian variable, or Lagrangian mass variable. And one can lift both symplectic structures described previously to this backward transformation SVPL, which is noted as SVPL here. The lifts of the obtained symplectic structures coincide and are generated by the following operator, which is presented here. Then one can consider its naive extension to jets. It means that we consider total derivatives operators on jets, not their restrictions to system of equations. And this operator, adjoint operator to this operator, is a variational operator for the SVPL system of equations. But this operator is degenerate in the sense that it do not lead us to a variational formulation which coincide with the initial system of equations. I mean that solutions of the Euler-Lagrange equation, which can be obtained using this operator, are not coincide with solutions of the initial system of equations. So let's consider another example. Consider trivial bundle, and let L be a function which depends on finite number of arguments of the form x, t, u, and derivative of u with respect to x of some orders. Denote Euler operator of L by H, then, as we know, we have a relation that linearization of H equals to its adjoint. And one can consider the following system of equations in an extended Kovalevskaya form. In effect, it looks like a system of second-order equations, of linear second-order equations, but here we have a function H which can depend on arguments of the higher order, which can be nonlinear, and so on. Then the system of equations can be nonlinear and not second-order system of equations, and so on. So, and direct calculations show that the following operator satisfies the relation for a symplectic operator. Let's consider its naive extension to jets. By naive extension, I mean such extension when we just using operators of total derivatives instead of their restrictions to system of equations. The adjoint operator to this operator is a variational operator for the system of equations under consideration. It can be, yes, it can be checked directly. And the corresponding Lagrangian for this system of equations has the following form, which is presented here. Therefore, delta generates an extendable symplectic structure, and more than that, the operator A adjoint is a two-sided invertible C differential operator, which inversion is the following operator. This operator is C differential operator 2. So we have a variational operator which is invertible. Thus, system of equations A adjoint of f equals to 0 had the consequence f equals to 0. And solutions of the initial system of equations and of the system of equations which we obtain by using variational operator are coincide. So delta generates an extendable symplectic structure with non-degenerate extension. Therefore, so now it's convenient to define some operations for us. Let's define such operations. First of all, let's define operation of substitution of epsilon prime let we have a differential operator which acts from kappa of pi to kappa with hat of pi. And let's consider components of the restriction to the epsilon prime of a prime of derivative of u with respect to a u prime. Components of this homomorphism can be considered as components of unique element which belongs to kappa with hat of pi prime in naive way, way. And components of such sigma are linear in total derivatives of u with respect to a. Then for a unique C differential operator holds the relation sigma equals to sigma with wave of u prime of the derivative of u with respect to a. Then one can put substitution of epsilon prime to a equals to sigma with wave. Secondly, define an operation of substitution of epsilon to a differential operator. Using local coordinates, it's easy to verify that for a C differential operator A, there exists unique C differential operator B of the following form, such that holds B prime is equals to substitution of epsilon prime to A. Here, it's important to note that components of this C differential operator could be non-zero only if the corresponding index alpha n's is less than B is. So components of this operator B depend on internal with respect to epsilon coordinates only, coordinates on jets, but they are internal with respect to epsilon coordinates. And we can put substitution of epsilon to A equal to B. In effect, this operation is something like choosing of a special symplectic structure from the equivalence class, from the corresponding equivalence class. As we know, a symplectic structure can be described as an equivalence class of operators, of C differential operators. And this substitution is just a choosing of the most simple form of the operator which generates this simplex structure, in effect, in some sense. So here I should make one remark that for some C differential operators holds the following relation: the difference between A prime of derivative of U prime and the substitution of epsilon prime of U prime derivative of U prime with respect to A is a sum of the operators of the yes, it is a sum on the right hand side, which is presented here. And since derivative with respect to A of f prime equals to linearization of f prime of U prime of the derivative of U prime with respect to A, then also holds the following relation, and hence we have the relation between restrictions of A and substitution of epsilon to A. It's important to notice that in effect, if we will prove that A and S epsilon substitution of epsilon to A are both generate symplectic structures for our system of equations, then these symplectic structures coincide in effect. Of course, these operators represents the same equivalence class in such case. And in effect, we will prove it further. So, and thirdly, we need to define an operation of a naive extension. It's just extension in local coordinates. We change internal coordinates to their analogs, which are coordinates internal with respect to epsilon coordinates on jets. And instead of restrictions of total derivative operators, we use just total derivative operators. So it's operation of naive extension in effect. Let's denote it by extension of jets. So now we need for the following fact which was proved previously in previous works. Let G be an element of the module of the adjoint module to kappa, then holds a criterion. Linearization of G is self-adjoint if and only if, for some horizontal form, its pairing of G prime with the derivative of U prime with respect to A is an exact horizontal form. For some horizontal form, this pairing equals to horizontal differential of this form. Then for any C differential operator, hold the relation, and that's why.
Kostya,
Yes.
простите, lambda n-1, I think, yes?
Lambda n-1?
Omega.
No. Omega is the horizontal n form because for a prime system we have dimension.
You have another one, yeah. Okay.
Yes, and it's an important fact. It's important for us, in effect, because this makes rather more simple proof of the main theorem I'd like to tell today. Rather more simple. It becomes rather more simple, in effect, I guess. So then this criterion can be generalized in the following way. If we put G equals to A adjoint of F in this relation, in this criterion, then using green formula, one can obtain that another criterion holds. Linearization of A adjoint of F is self-adjoint if and only if for some horizontal n form on pi prime. The result of the pairing of A prime of U of the derivative of U prime with respect to A and F prime is horizontal differential of this form omega. So let's talk about the analogy with tangent covering. This criterion can be rewritten in the following form, where G is the element of image of Euler operator if and only if there exists some horizontal n form such that hold the following relation. This criterion is related to a Noether identity which can be written on jets, on the initial jets of pi. This Noether identity is just a particle case of the green formula, of the well-known green formula. If one put to the green formula linearization of Lagrangian L as an operator, then one can obtain the following identity. It's so-called Noether identity, in effect. Here, E with low index Q is an evolution vector field, is a symmetry of jets, in effect. And W is some horizontal n-1 form, n-1 because we wrote it on jets of pi, not of pi prime. Then if we will formally substitute here instead of Q the derivative of U prime with respect to A and consider wedge product of this relation by differential of A, then here we will have something like left-hand side of, then on the left-hand side we will have something like pairing of U, of the derivative of U prime with respect to A and G prime. Here, Euler operator of L is G prime. And the right-hand side became a total horizontal n+1 form, in effect. So this criterion, which we discussed previously, is just another realization of the Noether identity on the initial jets. So, and here I must recall that we have the following fact. If a conservation law of a system of equations, of any system of equations in an extended Kovalevskaya form, has some global characteristic, then it also admits a global characteristic such that its components depend on internal with respect to epsilon prime coordinates only. It's so-called, it's lemma from Martinez Alonso work, and it's simple lemma in effect. It uses the fact that characteristic function of characteristic of some conservation law it's pairing. In fact, it's pairing with the left-hand side of the equation.
Sorry, what is global characteristic?
By global characteristic, I mean characteristic which is defined on jets. Global characteristic is such vector function or such section such that it's pairing with f, where f is the initial system of equations, equals to exact horizontal form.
Okay.
So in some sense, it's a extension of the characteristic, and it's non-uniquely defined. It's non-uniquely defined, but it's not a problem for us today. So we need here the fact that if a conservation law of a system of equations in an extended Kovalevskaya form has some global characteristic, then it also has a global characteristic which components depend on internal with respect to epsilon prime coordinates only. And therefore, from the relation, from the condition of self-adjointness of the linearization of f adjoint of f, of a adjoint of f, it follows that the following condition holds: they exist and horizontal n form omega such that the result of pairing of substitution of a prime to a, which acts on the derivative of a prime to a, and the result of pairing of this construction to f prime equals to horizontal differential of omega of some form. It follows directly from this fact, from the Martinez and Long's lemma, if you want. Of course, this substitution of epsilon prime to a, which acts on the derivative of a prime, u prime with respect to a, is just a substitution of external with respect to epsilon coordinates to the right-hand side of the conservation law. So it's just a substitution to a characteristic of a conservation law. As we noticed on previous pages, variational operators could be described in terms of characteristic of conservation laws, global characteristics. Here we have in the last row we have a pairing of u prime of something with f prime, and the result of this pairing is exactly horizontal form. It means that we have a conservation law of f prime in effect, and a prime of the derivative of the u prime with respect to a is a characteristic, global characteristic of this conservation law. So we have a variational operator for the system of equations if and only if its prime version, which applied to the derivative of u prime with respect to a, is a characteristic of a global conservation law for system f prime equals to 0. So variational operators are directly related to conservation laws of prime system. In fact, this conservation law is a conservation of Lagrangian, of the initial Lagrangian. Then we have just Martinez-Alonso lemma, and from it follows that self-adjointness condition implies the fact that for some horizontal n form omega, the holds relation, the following relation, which is presented here. But from this fact also follows that linearization of substitution of epsilon to a of the adjoint operator, of the action of adjoint operator of substitution epsilon to a, its action to f, is a self-adjoint operator in effect. And we obtain the following theorem. If we have a variational operator a adjoint for a system of equations epsilon in an extended Kovalevskaya form, then such substitution of epsilon to a, then adjoint operator to the substitution of epsilon to a, is also a variational operator for epsilon. So in effect, it means that each extendable symplectic structure, at least each extendable symplectic structure, can be represented by the operator of the simplest form, always. And the naive extension of this operator, which has the simplest form, is always a variational operator for a system of equations. So if we have a system of equations in an extended Kovalevskaya form, then symplectic structures, at least extendable symplectic structures, are related with variational principles in the most simple way. And we have two necessary corollaries, and first of them is a C differential operator of the following form generates an extendable symplectic structure of epsilon if and only if it satisfies the system of equations, which is presented here, the system of equations 4. And the second corollary is that each extendable symplectic structure of a system of equations epsilon in extended Kovalevskaya form is generated by some operator of the form 3. It's important to notice that, again, components of this operator in local coordinates could be non-zero only if the corresponding relation holds, only if alpha n's component of the multi-index alpha is less than BE, B is lower index E. So this theorem and corollaries from this theorem gives us complete description of all extendable symplectic structures. In effect, we have complete description of all locally extendable symplectic structures. It was written in the Igor Khavkin's work, as I remember, but they were described in terms of differential forms, not in terms of differential operators, in effect, C differential operators. Now we have a simple way to check if our symplectic structure, if our symplectic operator is related with an extendable symplectic structure, and we have a simple way to obtain a variational operator from this symplectic operator. In effect, it is a naive extension of the simplest operator which represents this symplectic structure. So what about non-degenerate extensions of symplectic structures? The following proposition shows that one can obtain extensions of a trivial symplectic structure using Lagrangians of a special form. We discuss here trivial symplectic structure extensions because if two symplectic structures, if we have two extensions of a symplectic structure, then they differ by an extension of a trivial symplectic structure. But there are too much extensions of a trivial symplectic structure. In effect, if we have an arbitrary operator which acts from cup of p to pi to its adjoint module, then Euler operator of the pairing of such nabla of f and f is related to a variational operator. So there are too much variational operators in some sense. However, in the context of the inverse problem of the calculus of variations, it's important to find non-degenerate extensions of extendable symplectic structures if it's possible. That's why we will consider question, what about non-degenerate extensions? So let we have a non-degenerate variational operator for a system of equations, for an initial system of equations, A adjoint, and let's denote a result of substitution of epsilon to A, in effect, restriction of substitution of epsilon to A by delta. Then for some C differential operator holds the relation f equals to B of A adjoint of F, and hence the linearization of epsilon equals to the following composition of operators. System of equations epsilon is L normal, and then we obtain the relation which states that composition of restriction of B to epsilon and of restriction of A adjoint to epsilon is the identity operator, in effect. Since this operator generates a symplectic structure for epsilon, then there exists some self-adjoint C differential operator square such that holds the relation, such that restriction of A to epsilon equals to delta plus square composition of linearization of epsilon n square in this operator. Thus, we obtain the following relation for the restriction of b to epsilon. We denote it by nabla. The relation, we have the relation 6, and hence we obtain the following relation. Operator of on the left hand side is self-adjoint. Then nabla satisfies another relation for C differential operators. I guess that in effect it means that nabla is a Hamiltonian operator, but I did not check all conditions at the moment. But it looks like it's a Hamiltonian operator. It must be Hamiltonian operator, I think. Then from the relation 6 also follows that this composition, which is present here, is also identity operator. And then we have another one identity operator. Another one relation. We have a relation 7, which we can lift to the cotangent covering. Its lift becomes a composition of delta and nabla adjoint, a result of an action of this composition to p equals to p. Here p is a non-local variable, is a fiber-wise variable for cotangent covering, and the wave means lift of operators, of the following operators. Components of this homomorphism are linear in p and its derivatives. Then for some C differential operator of the simplest form, of the analog form which we described, this form is analog of the form which we described previously. And for some operator of such form also holds the relation that adjoint to nabla, action of the lift of the adjoint to nabla to p equals to lift of zeta of p. And hence we have the relation 8. Thus we obtained a necessary condition for a symplectic structure to have a non-degenerate extension. And now let's assume additionally that the initial system of equations is a system of evolution equations. Then this relation implies another relation. It can be checked in local coordinates. It's a quite simple check, verification in local coordinates, that this relation implies the relation between extensions of these operators, not lifts, but just extensions of these operators to jets. And hence we have a relation between extensions of adjoint operators to jets, but delta is a skew adjoint operator. Then the relation 9 can be written in another form, and then it means that the extension of operator delta must be two-side invertible operator in effect. So we obtain the following theorem. Let A adjoint be a non-degenerate variational operator for a system of evolution equations, then substitution of of epsilon to this operator, then the adjoint operator to substitution of epsilon to this operator is a two-sided invertible variational operator for epsilon with a C differential inversion. In symplectic structures, sometimes, but by symplectic structures for evolution equation, we mean operators of a simple form, not equivalence. This operator substitution of epsilon to A is the most simple representative of this equivalence class. And this theorem means that the obtained symplectic operator is related to extendable symplectic structure which has non-degenerate extension if and only if it's two-sided invertible variational operator for equations. Thus, symplectic structures with non-degenerate extensions for a system of evolution equations are completely characterized by two-sided invertible C differential operators of the simplest form, which satisfy the system of equations. And this system of equations, its solution is operator delta, and the condition of an operator to be symplectic operator in effect. And we may solve this equation, and then we may throw away unnecessary conditions for which this relation is not true. And last remark, we have a scalar equation in extended Kovalevskaya form. Then for composition of any C-differential operators, delta and nabla holds the following relation between their orders. And hence, in this case, we obtain from the relation the composition of the restriction of B and A adjoint is identity. We have that each non-degenerate variational operator A adjoint, its restriction must be of order 0. Then substitution of epsilon to A adjoint is a 0 order non-degenerate variational operator, and the component of this operator depends on internal with respect to epsilon coordinates only. Thus, if a scalar equation in extended Kovalevskaya form admits a variational formulation, then B is even number, and in this case, each symplectic structure with non-degenerate extension has a 0 order non-degenerate extension. So we need not to consider symplectic operators of non-zero order for scalar equations if we want to obtain a non-degenerate symplectic structure in this sense. Oh, and as a conclusion, I must say that application of the result of led to a complete description of extendable symplectic structures, in effect in terms of operators, for systems of equations in an extended Kovalevskaya form. Besides this, the obtained results allow to describe all extendable symplectic structures with non-degenerate extensions for systems of evolution equations. And the obtained description is related to the problem of constructing inversion operator. However, in general, calculation of extendable symplectic structures of all orders is a non-trivial problem by itself. So, in effect, what can I say in effect? This work shows that if we have an extendable symplectic structure which is generated by some symplectic operator, then it has a variational extension of the simplest form, always extension of the simplest form. Simplest form is what is the simplest form? It depends on local coordinates representation, but systems of equations in an extended Kovalevskaya form, in this sense, they are similar to evolution systems of equations, and they have, in some sense, they have the most representation in the coordinate, in local coordinates, and this fact allows us to use some operations of extension. And if we have a symplectic operator which generates a symplectic structure such that this symplectic structure is extended, then its extension can be obtained by the naive extension of the simplest operator which represents this symplectic structure, which represents this equivalence class of operators. So in some sense, it means that extendable symplectic structures, at least extendable symplectic structures, can be described in terms of operators, of the simplest form operators, instead of equivalence classes of operators. But this description depends on local coordinates, of course. And for systems of evolution equations, the simplest operator, naive extension of the simplest operator, must be non-degenerate if we want to see a non-degenerate symplectic structure. It must be two-sided invertible operator. So I'd like to say thank you to Professors Alexander Vasilievich Aksionov, Ivo Semyonovich Krasechik, and Alexander Moiseyevich Verbovetsky for constructive discussions and for everything. Thank you very much for your attention.
Thanks a lot. Let us thank the speaker. Any questions?
I have a question about the construction of prime equation.
Okay.
Do you think that it's invariant construction?
Invariant. What do you mean by invariant? I'm sure that.
So we took a differential equation and produce a new equation.
Yes, yes. It was described previously. I'll try to find it. Its invariant description is written here, in effect. Here and here. It's just similar to a construction which we used when we talk about system of evolution equations, in effect. But for systems of evolution equations, on the left-hand side is derivative of u with respect to time, and on the right-hand side is something which is independent of derivatives of u with respect to t. And this construction is similar to the right-hand side construction. In fact, when we talk about evolution equations, we have a section which is independent of t, and then we assume that there exists another one independent variable t. And we write down something like the derivative of u with respect to t equals to phi, some section. Here we have absolutely the same construction, but we do not write down something like on the left-hand side, the derivative of u with respect to a equals to the right-hand side. It's just a section, it's analog of a section phi without the left-hand side, in effect. We make phi equal to 0 in this sense. The analogy between this construction and the construction which we about systems of evolution equations is, in fact, it's a direct analogy, but introduce left-hand side equation, we just write that on the right-hand side, the right-hand side equals to 0 in some sense.
Okay. And do you think that you use somewhere in proofs derivative with respect to this new variable a of more than first order?
No. Yes, you're right. It was not any derivatives with respect to a of order more than 1, and that's why this construction can be represented in terms of tangent covering. However, the last step, this lemma of Martinez-Alonso, works in a simple way. It works for us for this construction of prime system, but analog of this lemma for a tangent covering, for usual tangent covering, is more difficult, I guess, because for a usual tangent covering we have just dimension of the base equals to n, not n plus 1, and in the Noether identity we will not have an exact horizontal form. And I guess that some technical details, we need for some technical details to prove the analog fact in terms of a tangent covering only, without the. So this prime system is not so necessary, I guess, for the proving of this. But it's just more convenient in this situation because it allows us just to say that from some more Martinez-Alonso lemma and nothing else. We need not to use nothing else, something else.
No, I think that for tangent covering, if there are no variables of order more than 1, then they're completely identical, because on tangent covering there is canonical vector field which corresponds to the RAM differential.
Yes,
and the only difference is that in tangent covering, it's usual not to include this vector field to a Cartan plane. And in prime system, you include it in Cartan plane, but it's still some distinguished vector field. So in any case, you have n-dimensional plane and a canonical vector field. And include or not include is a matter of convenience.
Is in this, yes, but for such situation, we will not have an exact horizontal form on the right-hand side of the Noether identity. Because E with a low index 2, this vector field, action of this vector field to Lagrangian is not non-exact form, as I guess. But if we will multiply it by which by differential of A, it becomes an exact horizontal form too.
But can we tell the following? We have an equation with symplectic form. Symplectic form means conservation law on tangent space, or okay, let it be tangent space. And then the tangent space is also in Kovalevskaya form, so this conservation law, its characteristic can be extended. And that's all. It gives us an operator.
Yes, it will be a variational operator in the simplest form. If it depends on internal with respect to tangent covering coordinates only.
Yes.
Then its naive extension gives us a variational operator.
Okay.
Yes, here a construction of this in effect. It just makes the proof simpler, I guess. Maybe I'm not right in about this. Maybe I'm wrong about this. In effect, we use construction of a tangent covering.
Okay, thank you.
Thank you.
More questions, comments? Well, if there are none, let us thank the speaker again.